individually. Sorry, the DG is working individually with some connected load, and the switch or the piece from the PCC, if the switch is cut out, so at that time we can say that this is islanding. So it is a phenomenon in which the utility grid is disconnected, whereas the distributed generator connected with the microgrid continue to supply the power to the load. Obviously, if it is disconnected and DG still supplying load, means uh, the line or what, they are still energized. Okay, so at that time what happened? There are several effect. Okay, and it can be detected, it should be detected within 2 seconds, otherwise many problem will arise. Okay, and the problem may be the we can say that the fault, or we can the substation failure, equipment malfunctioning. Okay, and it is urgency to detect this islanding with an accurate manner. For what? The voltage and frequency fluctuation, it will be there. The utility line worker, they are working, and if the islanding is unintentional, if islanding is intentional, that is okay. To maintenance, the utility engineer, they do islanding, that is different. But if this is unintentional islanding due to other fault or all those things, then it will be the line worker safety is very important. Then the equipment related, to protect the equipment may be harmed, so at that time also this is important to detect the islanding. Then it can be hamper the automatic restoration. Once islanding is occur, then automatic restorations is also important. So before also islanding is detection of islanding is important. So this is one method that has been published, one conference that is in 16 actually. So this is the method that we have used. Means this is a very basic method, that is the wavelet transform has been used. That is, the data is simulated, the voltage data that we have collect, the three-phase voltage data. Then we applied the sequence analyzer to extract the negative sequence voltage. Then we have applied the wavelet transform to get the approximate and detail coefficient. And this approximate and detail coefficient, then we formulate different features, that are the energy, entropy, standard deviations. Okay, and these features are in a vector, are are inputted to the machine learning technique to decide whether this is islanding condition or non-islanding condition. So to doing this work, actually first is to simulate the model, second the gather the data with related to the islanding and non-islanding individually. Okay, so this is the model that we have simulated. This is a 2DG model, 2DG. Okay, and here you can observe the pi line are there, and different circuit breaker are connected. Okay, and different load are there in different position, capacitor is there. So 9 cases including islanding we have simulated. First one is the islanding. Okay, so islanding is the first condition. So islanding, how we simulate? One is, if you observe the diagram, then you can see, if first situation, if the circuit breaker 1 is closed, circuit breaker 5 is closed, but we switch the circuit breaker 2, sorry, circuit breaker 4, then the DG1 will be islanded. If switch the circuit breaker 5, then DG2 is islanded with a load. L4 is the load is connected with this. If we switch the circuit breaker 2, then at that time what happened? DG1 and DG2 both are islanded. Okay, so these are the islanding scenarios we have closed, means we have formulated. And here many samples are, we means many signals we generate by varying the loading condition. Means the L3 and L4, we can, by varying all those things, we simulate many cases for islanding. Then the non-islanding cases are like different cases, like transient period, like fault condition, the single phase fault, double line fault, triple line fault. These are the three cases. Then sudden load changes without islanding. This is sudden. If we change the load, means we can add or subtract some load. Then this is the fourth condition. Then this is the capacitor switching. This is another transient condition that is not islanding, but it can behave like a island. Then sixth is the DG tripping case. If DG1 is islanded and DG1 is islanding, and we are collecting the data from the DG2. Okay, so DG2 is not islanded. So at that time, for DG2, we can say that this is non-islanding condition. If we are collecting data from DG1 and DG2 each islanded, at the time we can say that DG1, for DG1 this is not islanded, like this. Then the 7th and 8th condition is the power quality. Some power quality event like voltage sag and swell, their signal also like similar to the islanding cases, so it may maloperate other relay. Okay, so here also we have simulated non-islanding condition. This is 1, 7 and 8, voltage sag and swell. Then we extract the features, the multi-resolution analysis we kept, as I already mentioned, that is the approximate and detail coefficient. So here we put the DWT, and here three set of features are extracted, the energy, and this is the energy that we have calculated through the square of the detail coefficient, summation of all the detail coefficient, and standard deviation and the entropy that we have calculated. Entropy is put we have calculated only the last, mean the fourth decomposition value, fourth level. Okay, so these are some visual means of the signal. This is the original negative sequence current during islanding, and this is the dB4, each were the mother wavelet of the wavelet transform that we used, and we have applied the fourth level decomposition, means and here you can see the approximate and detail coefficient for all this level. And this is the line to line ground, double line to ground fault, and this is the dB2 mother wavelet we have used. dB4, this is islanding condition. This is the double line to ground, dB2. This is the voltage sag. You can see the two, means the time of voltage sag, means about 1100 to 1400 around. This is the upper voltage sag. Okay, then we have applied different machine learning technique. Okay, so here first one is the uh, this table shows the for dB2 wavelet. Okay, and here first we make one decision tree actually. By this is manually we made, not any tool, machine learning tool we have not used. Means we have just calculated all the values. So here we calculate the maximum value and minimum value of energy, entropy, and standard deviation, and we manually we fix this value, and we make the decision tree. This is the, if f1 is less than 0.007, then this value is LLG, line to ground, double line to ground, triple line to ground. If f1 value is greater than this, and like this, we make the decision tree by observing only maximum minimum value. Then this is the excuse me, I'm audible? Am I audible?
Yes, sir. It's audible only, sir.
Yeah. So this is the confusion matrix. So here about 133 cases for islanding and about 532 number of sample for non-islanding we have generated, and different mother wavelet. This is the confusion matrix. Means dB2, dB3, dB4, dB10, R wavelet, COIF3, COIF5, SYM4, 8, 10. We have taken about 10 mother wavelet to compare what are the performance in wavelet transform also. And here with the decision tree with 30 dB noisy cases. In the noisy cases, we can see the false positive and false negative cases are increased for all those things. After that, we calculate the accuracy, dependability, and security from this. So here we can see the precision, dependability, security, accuracy and F1 score we have calculated for all mother wavelet, and we find this. And here we can observe with maximum accuracy we got about 99.54 with db3 mother wavelet. And after that we applied the neural network, the basic neuro ANN structure we have applied, and here also we got the accuracy. Here we found 100% accuracy in most of the case in noisy condition, without noisy condition, and 30 dB noisy condition it is decreased. Okay, so in the decision tree that we have made previously, it performed about 99 point something, but here it is 100% accurate. So we have applied an SVM, support vector machine, and this is the some comparison of the accuracy and F measure or F1 score that we have compared. And here we found about extreme learning machine in this perform better compared to other. And these are few other islanding related work that I have worked and published, like IEEE System Journal, then the international transaction electrical analysis. See, what here in the IEEE paper we have applied the dual tree complex discrete wavelet transform and one XGBoost algorithm with SMOT. Actually, this is published 2021. Another, we use the other signal processing technique like variational mode decomposition and subspace k nearest neighbor, that is one ensemble learning. And another loss of man, loss of man islanding, also known as the loss of man. Okay, so loss of man detection in and here also we applied different technique like more mathematical morphology, all those things. And these are different papers that we have published, all are with good impact factor journals. Then another case, the third case study that I am going to explain, that is the microgrid fault detection and classification that I have worked. Okay, so uh, as we know, microgrid is what? Microgrid with its well-defined operational boundary comprise the uh, distributed energy resources, energy storing devices, and controllable load. Then uh, it operates in grid connected mode and islanded mode. As we know, microgrid may be operated in grid connected mode and islanded mode. And the variation of current in grid connected and islanded mode each different. So the protection, to apply the protection in both grid connected and islanded mode, it is very difficult. Okay, then we can say that microgrid brings several benefits like economy, security, reliability, resiliency, power quality, and reduced environmental pollution. So so and it brings different technical challenges, like as I mentioned, the grid connected and islanded mode, the current behavior is different. Okay, so it is difficult to maintain. Then again, in the microgrid, this is the power is bidirectional, so here also providing better protection algorithm, it is difficult. So here an overcurrent relay may misoperate or miscoordinate due to what? The fault current level in the islanding mode. Then we can say that the distributed energy resources, the DGs may be synchronous based, may be inverter based, and at that time also the fault current contribution is different. Then and due to the fault current level as it is changing, okay, the traditional overcurrent relay, if we apply it, then it may maloperate. And again we can say that to make these systems protect. Okay, so here we have applied different machine learning techniques. So this is one paper that I'm going to explain, that is the MODWT, maximum override discrete wavelet transform and XGBoost algorithm that we have applied for smart energy solution for fault deterrence classification in microgrid. This is published in the applied energy with an impact factor is around 11. So here main thing is there. Here we have designed the microgrid protection scheme MPS, which satisfy these criteria. A common protection strategy that can affect both islanding and grid connector mode, it can be applied. Second, the microgrid protection scheme must first and ensure minimal area of disruption of power supply. Third objective we have put, it can be useful during the high impedance fault. As we know, if the impedance value will be increased, the resistance value will be increased, the fault current variation will be decreased. And at that time, for a small amount of fault current, then also the our systems will work. Then again, this is important, the primary and backup. If primary failure, then backup should work. Okay, so we have designed such that it can operate in both primary and backup protection also, and it can be effective under extreme noisy environment. So this is also one objective, and all those things we maintain with standards. Okay, so here we have designed the contribution word. We have designed an XGBoost. Here machine learning technique that we have used, that is XGBoost, and the signal processing technique that we have put, that is the MODWT for the features extraction. So I'm just skipping. I've already mentioned. So here actually, uh, this is the IEEE IEC microgrid. This is we have simulated in MATLAB environment, and here actually 4 DG we have kept. Okay, so here 1 DG each type 4 wind, that is the inverter based, and one hydro turbine generator we have used. Another DG is the DFIG, that is the induction base induction generator, and one is normal wind. Okay, so 4 type of DG that we have used. And here you can see the dotted line. If this loop is closed, so at that time what happened, it the power will bidirectional. Okay, and at that, and it will be like a mesh network. Okay, means, so we tested the system with radial network also, and with the meshed or ring based system also. Okay, so here this is the total systems that we have used, like this is differential protection. Okay, so here like boss R S sorry, R S and Q are there, and if fault each occurred in the line 1 DL1 for example, here we take the current from the CT Q2 and CT R1. We collect the current value, and we extract the signal processing. We apply the signal processing, and we calculate the features, and we calculate the difference, and we this value is inputted to the machine learning technique for training and testing. Okay, for all those things, what these things for the primary protection. Okay, and another similarly also the machine will be trained with taking the data from S and Q. Okay, and that data is calculated the difference, and here we can say that this is for the backup protection. Okay, if the primary will fail, then other algorithm will work. So here from the MODWT, this is the maximum overlap discrete wavelet transform. So this is the normal flow chart of the DWT 3 level, and this is the below diagram is the 3 level MODWT. Okay, so here in the previous high pass and low pass filter are connect with soft sampling, and here actually there is no here actually we applied the wavelet coefficient W1, the scaling coefficient we have applied. Okay, so here wavelet coefficient, this is the equation, and scaling coefficient, the equation are there. Then this is the some visual waveform that the MOD decomposition value, that current, the IA, A phase current, and we applied the 3 level decomposition, and we calculate all the coefficient value, means the approximate coefficient and detail coefficient. One approximate, last approximate on all three detail coefficient. And this is the AG fault. This is for the a G fault occurred at 0.3 second line D1. Okay, so this is also. Then these are the features that were calculated. The energy value we have calculated for line for A phase, B phase, C phase, and zero sequence also we have calculated. For the zero sequence component also we calculate the energy value, and the zero sequence will be help to get whether this is ground fault or not. Means this is line to ground or line to ground or not. That will help by the zero sequence. And for primary protection that we have calculated, that is the energy of xlq. Here x represent the abc all this phase value minus the other bus, means between the two bus we have calculated, and this is the that I've already explained about the backup protection. So here, this is the system that we have generated. That first we pre-process the signal, then we calculate the MODWT energy calculation. These are the features detection, and for phase identification, we use all those things. For detection, we have used for the line. Okay, means phase means whether this is A phase fault, B phase fault, or C phase fault, that can be detected by this. We use the zero sequence. So here again, to provide the primary and backup protection, we simulate the signal like in this system. Actually the bus from bus 2 and 3, if line 1, if the fault is occur at line 1, we collect the data from 2 and 3. Okay, for primary protection. And for the backup protection, for the same fault, for same line, we collect the data from 3, 1, 2, 6, 3, 5, or adjacent, all possible adjacent value we have collected. Like similarly to for the line 2, line 3, line 4, line 5. And for the, if it is mesh connector or this is loop like structure, then obviously our nodes will be increased. So at that time we collect data from with widespread. Then fault we have taken, fault that we have taken about different type. At fault is occur 10% of the line, 20% of the line, 30%, like 90% of the line. Okay, and with the different variation of inception angle, and for both grid connected and islanded. And again the high impedance fault also we have connected, means we have generated that is 90%, 10% to 90% of fault location. And here the resistance value we have changed about 1000 to 1400 with a high value of resistance value, and inception angle also we have changed. So these are the different conditions that we have, all possible condition. Means condition 1 is grid connected, primary protection and radial. Condition 2 islanding, primary protection, radial. In this way we divide different condition for this analysis, different 8 condition. Okay, so these are the features that we have generated. The energy value, energy level of the first level, energy level of the first level, and this is the differential energy. This is the we can say that the from the CT2 or bus 2 we collect, and bus 3 if line 1 fault, and we differentiate the energy value, then we get the diagram like this. Okay, then for the third level energy value, this is see the energy value of the C2 and C3, and see the difference. This is the second level coefficient. In here also we calculate the difference like this, and see here actually if this is high impedance fault, low impedance fault, or no fault condition. Here you can see for the black color line, it shows the high impedance, blue is the low impedance, and the green color is the no fault condition. So if the fault is occur here, A phase, here fault is occur low impedance fault, A phase fault. So see the variation in green, sorry, the blue is higher. Okay, so here similar the differential energy of for the second level, you can see all those things, and the different energy for the third level coefficient, here green is the low impedance fault, here also it is higher. Similarly, this is the AG fault, sorry, AG fault. So here also we have calculated like this. Sorry, this, oops, then this is the whether this fault is A phase, B phase, and C phase. Here the phase is here the AB fault. AB fault. So you can see the red line is the C, and the C value is very less. Okay, very less with compared to AB fault. See here also this is the fault is AB to ground fault, and here also you can see the red line. This is C value, the energy value. This is approximately 0. And here this is AB fault. This is also you can see now if ground involved or not. So here we took the zero sequence, and in the zero sequence, if calculate the difference for the first level, second level, and third level, all this level, you can see uh, during AB fault and AB to ground fault. Here you can see the AB fault. If this is ground is not involved, then this value is this difference value is differential energy value is approximately 0. We got okay. So it is easy to differentiate. After that, we applied the XGBoost for classification, and here we obtained the accuracy of 99.17%. Uh, for condition 1, for condition 2, we obtained 98.33. For condition 5, we obtained 99.17, like this. And this is the different all condition. This is the accuracy value. I'm not going through detail all this value only. Okay, and if we differentiate the phase, then this is the classification result during the condition 1. Here accuracy is 92.12, like this. These are the results only. So we applied, and here also we obtained. Okay, then after that, we as we know all this, to generalize the model, better to put in another model. So here IEEE 13 bus microgrid test model, we tested these things, and we obtained this result. For islanding overall accuracy, we got about 91.28%, and in the grid connected mode, the overall accuracy for the protection we got about 90.53%. And again, in the real time systems, actually here we have used one digital signal processing kit, and here actually we the algorithm that we have designed, that algorithm we put in the kit, and we test our systems. So in a software in loop like structure, and we also verified our result. So where the accuracy is approximately same as we got earlier. And few other microgrid protection work also. This is different method that we have applied. So this is one IEEE systems journal we have applied the dual tree complex tolerance mode and exhibit for these are the thing. This is one microgrid protection that we have got on IET generation transmission distributions, applied energy, and scam journal, and international advanced mechatronics. These are the other paper that we have published on different signal processing and machine learning techniques. Here we have used actually extreme learning machines, XGBoost, and other machine learning technique. Then another case studies we can say. So this is my last case study that for application. This is the fault detection in VSC HVDC systems. Okay, multi-terminal HVDC system. Here also, as all these things previously that we have discussed about what the AC distribution system. So here this is the DC distribution systems. This is the high voltage DC transmission system. So this is one paper published in the recent paper that we have published in 2024. For this is my PhD students' work. So this is the fault detection and phase identification in the VSC multi-terminal HVDC link with Stockwell transform and teaser energy operator, and it is published in the EPSR Elsevier. Okay, so overview of HVDC, if we say, then as we know the first HVDC system linked, that is the mercury arc valve that was designed in 1954. Then in 1960 the thyristor semiconductor valve replaced the mercury arc. Then 1997, the world first VSC HVDC systems will there. Then 2010, the world first 800 kV ultra high voltage DC links was installed in China. Then 2013, the hybrid HVDC breaker is played. Then 2014, this is one ultra high voltage DC installation like this. The HVDC history, we can say that. And the high voltage DC transmission, this is the various advantages with conventional HVAC system. Madam, I have still I have some 10 minutes time.
Yes, sir, you
Yep.
have time, sir.
Okay, madam, thank you. So here HVDC technology, so here it is from HVAC different benefit that we have already uh, know all those things. So I'm just skipping. This is secure and effective cost solution, then reduction in transmission losses, installation cost, then the transmit power over long distance. These are some advantage of HVDC. I'm just skipping all those things. Then these are the different issue and challenges of protection systems. So as we know, the mechanical circuit breaker with natural zero crossing and volt current to interrupt the fault. Okay, so with the absence of zero crossing in DC fault current, create the mass operate or many problem in providing a good protection systems. So in the DC fault current level considerably high and low voltage level across entire grid because the significantly low DC line impedance. So this is one challenges. Then again, location in DC grid comprehensively not easy because of low line impedance. And under some condition the voltage may drop to 80 to 90% with the nominal value, and this is the due to the blocking of the converter. Okay, so these are different challenges which make the protection systems difficult to apply. So actually, what are the kind of HVDC fault? So HVDC fault may be different type, like we can say that if we analyze the DC fault, one is the DC fault occur in the DC side of the HVDC system. AC fault occur in the AC side of the HVDC systems. Then the DC fault may be pole to pole, means the positive pole to negative pole, maybe positive pole to ground, negative pole to ground. Okay, maybe over voltage fault, maybe over current fault, converter side. If this fault is occur in the converter station, then this is the converter fault. In the valve, actually in the converter valve, if fault is occur, then converter valve fault. So different type of fault are there. So taxonomy of HVDC fault. So here if we analyze this, so is we just made a simple diagram here, a simple HVDC system. This is a two means the one is grid is there, two side the grid is there, and the voltage was converted, it is joining by 200-kilometer line. Okay, so here if you see, this is the this diagram shows the fault inception. Okay, means pole to pole fault. This is the case of pole to pole case fault with different uh, means if you say the different line with this different distance, different color shows the different 10 kilometer, 50 kilometer, 90 kilometer. Okay, how this it behave. Then pole to ground, if the fault is pole to ground, means either positive pole to ground or negative pole to ground, how it behave like this. See the after the fault inception. Okay, then if we plot all the magnitude, all those things, if plot the magnitude with respect to distance and with respect to the fault resistance, how the variation are goes, means a huge variation are there. So for this all huge, very high to very low, it is very difficult to apply a normal relaying algorithm and to with a threshold value to find out and to detect which fault is occur. Then it is very difficult. Okay, so to make this easier, we applied the signal processing artificial. So here the main objective is what? So see, why the HVDC protection, the AI algorithm or signal processing algorithm use. This is the diagram that is plotted. This is the overall paper published. Okay, overall paper published for HVDC protection only. Okay, you can see the blue line is the overall, and conventional is the green line. Okay, and AI and SP based technique is the red line. Okay, so AI and SBD is able, artificial intelligence and signal processing based. It is gradually it is increasing. Okay, means people are working on this. So this is important. And here in the table actually we provide, I mean, the advantage of signal processing AI technique and conventional. So accuracy in signal processing AI techniques, it is higher, adaptability is higher, fault detection time is faster, robustness improved, flexibility high, dependency less, computational complexity higher. Like this, it is many expect it is advantages than conventional technique. So here in this work, the main objective to carry out this research include the to read different AI and the signal processing HVDC. Then we simulate one HVDC system in MATLAB environment. Then design intelligent protection algorithm with signal processing techniques. So this is the work that I simply am going to here. Here we have applied actually we uh, we have applied uh, uh, S transform as a feature extraction technique, and the modified RNN we a deep learning technique, that is the GRU, get at reconnect unit. We design a bidirectional get at reconnect unit, not actual bidirectional. We make this as a bidirectional, and a teacher energy operator we have applied to fetch identification. So this is the model that the system that we have modeled. This is the 4 grid systems, 4 terminal symmetrical monopolar HVDC link. And here overall fault cases we have simulated our 3444 total number of AC fault, means AC side. This is the 2080, and cumulative DC fault 11,232. And these two are the, we can say that this is no fault condition. So if the fault is occur in the line 1, then this is, we can consider this is the DC fault. If the fault is occurred in other line but we are measuring from the relay 1, then we can say that this is a no fault condition or transient case for that condition. Okay, and this is the, if we plot all those things in a diagram, then this is the change in voltage after the fault and change in current maximum after the fault. And this is C, this is the how it is changing with external DC fault, external AC fault, and DC fault. So this is the methodology that we have designed for fault detection, and this is for the faulty phase identification. So here we have acquired the positive pole current and negative pole current for the 32 sample only, very small, means about one fourth. Okay, no, one half cycle of the window we have taken for the sampling frequency, as for the sampling frequency. Then we calculate the uh, modal transformation we have put, and we calculate the line mode current, line mode. Then we applied the S transform to generate the S transform matrix. But here the main thing is that from the S transform we have not calculated any, we have not put any statistical feature extraction from the S transform. We have directly put this as a image to the GRE unit. So this is a 17 cross 32 S matrix. So in, if you say that this is the modal transformer transformation that we have applied, then see, okay, so here if the fault inception, after the fault inception, how the positive pole to current, negative pole to current, and the corresponding ground mode and line mode component for the internal for the external fault and for the AC fault, how it behave. We have plotted this. Then here the polar plot we have plot for the line mode current. Okay, for internal DC, external DC, and external AC fault. So here, if you say the visible distance apparent from the plot, that a logical inclination toward the waveform analysis within frequency domain, more precise in the time frequency domain for extraction of fault signature. Okay, so for this we applied the S transform, and this is the time frequency plot for the S transform. This is the heat map for the Stockwell matrix that we have generated, and this matrix actually we inputted to the GRE unit. So this is the proposed GRE unit that we use. This is one the different layer. These are the different layer. That is the input. After that, flip one flip layer we have used. Then GRU unit, then flip, then concatenate. We concatenate both these things. Then GRU3, then flip, then GRE4, like this. Softmax layer, all those things. And these are the different activation function and the filter parameters. Then this is the result and discussions for the, this is the fault detections. So here this is the box plot. We can say the with respect to the frequency and the amplitude. This is the value for different external fault, internal fault, and here you can see the total proposed method. Here the sequence input layer. This is flip. Then this is the GRE unit, means layer by layer how the system is work inside the GRU. This is shown, and last one the softmax layer. Then the fault detection. This is the training accuracy, validation accuracy, and training loss, validation loss we have plotted, and approximately for the 50 epoch. And this is the performance. We got the accuracy without noisy condition. It's about 99.92%, and for the 20 dB, it's 99.02%. And for the phase identification, we have applied the TKD, the teacher Kaiser energy operator, and here you can see here the positive to ground, negative to ground, positive to pole, and positive now to ground. And here this is the thing that we have applied. And after that, all those things, this systems is simulated it in 13.5 kilohertz. Okay, but by changing the sampling frequency, how it impact also we have studied here. With a different sampling, means we reduce the sampling frequency to 2700 hertz to 3200, then 6550. And here also this is the with a different sampling frequency how the accuracy behave. Okay, then also we have tested with smoothing reactor. As we know, in the HVDC system, the smoothing reactors value, and the smoothing reactor value we decrease plus minus up to 30%. Okay, and we have tested with a different value, and we simulated the result. And this is the comparative with by LSTM, CNN, 2D ELM, then LSTM replacing GRU and proposed GRU method. And we found our accuracy is better. Then we also compare this method, all those things, with the previously published paper to show our efficiency, the method efficiency. So this is all about the HVDC fault detection. So these are the different things that that we have analyzed our power quality, one application, then the islanding, then the microgrid protection, then the HVDC protection. 4 different case of application for the signal processing and artificial intelligence. Okay, again, H for 2 minutes, just I'm just showing some few slide. I've already made many slides. So just uh, this all those things no means everything, the how the procedure as I mentioned in the initially, feature extraction, then selection, then classification, all those things, the similars can be done in the biomedical also. Okay, and these are some HVDC protection work that we have already published in many good journals. Okay, so like this, the industry in healthcare domain also, these are the some we can apply for signal processing in ML in biomedical signal detection, but it is already timed. So I'm just showing some slide actually for this. This is the biomedical signal. We have applied actually many things. Biomedical signal processing also we have worked in many things for PhD students. So different image we collect from the biomedical means for this is a gastro imaging. So here we applied the DWT, then we calculate the low pass high pass filter we have applied, then we put the image into the machine learning. This is like I think I'm out of time actually. Okay. So thank you very much for this. If anybody working on this domain and to want to work on this domain, they may contact me for this, for any issue or all those things. If you have any question, you may ask.
Sir, how do we select the techniques, sir? ML techniques, how do we select for a particular problem?
Particular problem, madam, that need to be means obviously for we need to analyze the different previously published paper first. Then for every methods is useful, but which method is best, that need to be depend on the data set, and what which kind of data set, how to formulate the data set, then means pre-processing. After pre-processing, every method will behave differently. So which method is best, it is difficult to answer actually.
So based on the previous like literature reviews, we can decide.
Yeah, previously literature review we can decide, but maybe that literature review for means that particular, if see madam, if we are working on a model, I am simulating one model from what means if I am working in the protection domain, if I have simulated the data with a large variation, some people have worked on a small variations, and their training is not that much that need. In some cases, maybe some normal method like normal ANN or normal decision tree also they perform good, but my cases maybe it perform bad. That depends, but overally we can say that uh, when we are working, we should first work on the state of art techniques, means that from ground level you need to go through that. After that you need to increase your complexity in the model to check actually.
Okay, sir. Participants, do you have any questions? Okay, sir, there is no questions. Can we, I wholeheartedly thank you for giving us a good lecture on this techniques. We could see
Thank
how much amount of work you have done in this particular area. And
Yes,
like, if there is any other forum, we can meet again, right? We would like to hear from you again, sir.
yes madam, thank you madam actually.
Thank you,
Another
sir.
thing is that I'm organizing one conference actually for this May. This is the third international conference on advancing in power, signal and information technology, APSIT. This is on the IEEE banner, and this is
Okay.
under the IAS, the Industry Application Society, that is sponsoring this. And
Okay.
if some participant or you also, if you want to apply any paper, then you can apply to this.
Yes, sir. Sure, sir. Sure, sir.
Yes, sir.
Yes, sir. Thank you, sir. Thank you so much.
Thank you madam.
Thank you,
Okay.
sir. We can wind up this session, sir.
Yes,
Can
thank you
wind up.
madam, thank you.
Thank you. Participants, you can take a break for 5 minutes. Kindly gather back at 7:45.